I'm Zhiheng from Institute of Computing Technology, China, and I'm going to present our recent work about subgraph matching. Okay, so firstly, let's talk about what is subgraph matching. We know that graph is widely used in the real world, such as social network, finance, and so on. And the subgraph matching is an important graph analytics task to obtain structured information. For example, in financial transaction graphs, we can do the fraud detection by mining the cycle pattern. The subgraph matching take one data graph and one pattern graph as input, and the goal is to find all subgraphs that are isomorphic to the pattern graph. In this example, you can see on the right that there is a one match graph for this 4-click pattern. Subgraph matching system usually adopt the set-centric paradigm. It contains two types of set operations, set intersection and symmetry breaking, to describe the connection relationship. For example, the vertex V2 in the pattern is the common neighbor of the vertex V0 and V1, which is expressed as the intersection of V0's neighbor and V1's neighbor. To find all matched subgraphs, the system executes the nested loop with set operations. Initially, the program starts from each vertex, and in each iteration, we perform set operation on matched vertex to generate the nested vertex results. So the search process is stateful, which maintains a search state and visits neighbors list for new search state. It continues to repeat this process until all matched subgraphs are found. If you use single GPU to accelerate subgraph matching, the usual approach is to load entire graph into the GPU global memory and then use the CUDA core to do parallel searching. On multi-GPU platforms, some work try to scale subgraph matching with many compute resources. That is, each GPU maintains the entire graph data and perform task parallelism. This approach can achieve high performance without communication, but single GPU memory limits the graph size, showing the poor scalability. Okay, some work try to use the CPU host memory to expand the scale of the graph data graph. So they build the K-hop subgraphs, which maintains the overlapping area and common vertex on CPU host memory, and then load this subgraph to different GPU for subgraph matching. The K-hop subgraph contains the required search state so that all GPUs can process tasks independently, but scalability is still limited by the CPU's host memory. In addition, different K-hop subgraphs share common vertex, showing huge redundancy. Okay, let's look at the third solution. For higher scalability, other works try to scale subgraph matching on partition graphs. As a price, frequent data fetching is required between different nodes. This solution sacrifices performance in exchange for scalability. In addition, currently there are only CPU data fetching systems like Zhiheng and Custo with poor performance. So how can we scale the subgraph matching with compute and memory resources? In this work, our goal is to push the speed and scalability limitation for subgraph matching. The problem we need to solve are the communication amplification and the low GPU utilization. Therefore, we propose Jupyter, a multi-GPU subgraph matching system. Firstly, we introduce a delegation mechanism to reduce the communication volumes. Secondly, we design the CPU-free system based on distributed shared memory, avoiding CPU involvement for higher performance. Finally, we propose topology-aware communication optimization to fully utilize the network bandwidth. Before we introduce our approach, let's see the subgraph matching example again. So we partition this data graph into two parts and put them on two GPUs. Now we need to match the pattern vertex 2 and the vertex 3. In this case, the search task is to obtain the vertex 7 and 1. Now, GPU 0 doesn't have the vertex 1's neighbor list in traditional data fetch mode to check whether vertex 7 is connected to vertex 1. We need to fetch vertex 1's neighbor list to local and then perform set operation on GPU 0. Finally, we can obtain the match subgraph 3671. However, the repeated neighbor fetching will cause a communication amplification issue, making the communication balloons 10 times that of the data graph. So why not send the vertex 1 and 7 to the GPU where the graph data resides, that is GPU 1. In this way, we can delegate the subgraph task to the corresponding GPU so that they can perform set operation locally. Since the task meta information is much smaller than the neighbor list, this approach can significantly reduce the communication balloons. In our evaluation, we find that the delegation mode can reduce the message size by 19% and the number of messages by 67% on average. For more details, please read our paper. Okay, let's see how the communication pattern changes. In the data fetching mode, different GPU exchange neighbor list, while in the delegation mode, different GPU exchange the search state. To achieve a task delegation, a simple idea is to write the data to the local memory buffer during each iteration and then perform an all-to-all data exchanging use CUDA-NICO. However, these methods require frequently CPU involvement, resulting in low GPU utilization. To solve this problem, we designed shared task queues on multi-GPUs. And each GPU maintains its own queues, and the other GPU can access remote queues. Now, GPU 0 is processing task 0 in local queues and have matching vertex 3 and vertex 6. But GPU 0 cannot continue match subgraph because of the missing neighbor list in local. So we materialize the search task into contexts, including required vertex information and operation types. Then the context can be serialized and written into the remote GPU task queues using only summary, get, and put primitive. After that, GPU 1 can read the local task queues and deserialize the context into the remaining search tasks locally. In the system design, we propose the topological message aggregation techniques to make full use of the bandwidth. We adopt different band size, CUDA communication calls, and hybrid communication scheduling intra and inter nodes. More techniques details are shown in the paper. Okay, let's put them together. Our system Jupyter maintains three components: delegator, executor, and the context manager. And the local workflow reads the data from the local memory and assigns tasks to executor for powering search on CUDA cores. Then executor writes the output result back to the local GPU memory. In the remote workflow, when executor discovers that the current task lacks the graph data to continue execution, it hands the task over the delegator. Delegator directs these tasks on the GPU where the data resides. After that, context manager serializes, groups the task, and directly writes it into the remote GPU memory. Okay, let's look at how Jupyter performs. We run most experience on 2 servers. One server is encrypted with 8 A100 GPUs, and another server has 6 nodes, each encrypted with 4 V100 GPUs. And we test 16 patterns and 8 datasets, including 2 large graphs, ClueWeb and UK14, with 14 billion each. Currently, other multi-GPU systems can only process graph with 18 billion each. We compare with 3 scale-up multi-GPU systems with GM, G2M, and PBE. And we also designed Jupyter Data Fetching, which is a CPU-free data fetching system of multi-GPUs. Okay, let's look at the end-to-end evaluation. The Jupyter performs much better than other systems in most cases. In end-to-end evaluation, Jupyter runs 122 and 12 times faster than PBE, VSGM and G2M on average. We designed the Jupyter data fetching to show how delegation performs. We can see that the delegation achieved a maximum execution time improvement of 6.6 times and an average improvement of 2.2 times. In addition, Jupyter can process 14 billion scale graphs in hours while other systems fail. And there are a lot of more results in the paper, and welcome to check it out if you are interested. To conclude, we designed a multi-GPU subgraph system to solve speed and scalability issues. We propose the delegation and CPU-free techniques so that GPU can handle larger graphs and achieve significant performance improvements. And our code is open source in the GitHub. Welcome to study it if you are interested. That's all. Thank you for your listening.